Welcome to your podcast for Lesson 28, Graphing Acceleration versus Net Force or Mass. After viewing the podcast, you should be able to graph the relationships between acceleration, mass, and net force, and also write an F-net equation specific to each individual problem to solve for an object's acceleration. For class tomorrow, I would like you to complete the warm-up. What is the acceleration of a 5 kilogram bowling ball when a net force of 25 newtons is applied to it? All right, from Newton's second law, we know that acceleration and net force are said to be directly proportional, right? And again, what that means is that when one goes up, the other goes up by the same factor. So if one doubles, the other doubles. If one triples, the other triples. So on the next slide, we're going to create an acceleration versus net force graph showing this relationship, with acceleration on the y-axis and net force on the x-axis. All right, so again, the relationship between acceleration and net force is directly proportional. So that means as one goes up, the other goes up by the same factor, or vice versa. If one goes down, the other goes down by the same factor. And so you can see a graph of this directly proportional relationship is going to be a straight line, and it's always going to have that positive slope to it. So we can pick a couple examples on here just to show you. So let's say, for example, net force is 2, okay? And if we follow that over, that shows us that our acceleration is a value of 2, okay? If we double our net force from 2 to 4, okay, according to our directly proportional relationship, that tells us that our acceleration should be doubled as well. And if you follow this over here, we see that it indeed is. This time, let's double our acceleration from 4 to 8. Okay? And again, we would expect that would cause our net force to double. And if we follow this down, we see that it does indeed double from 4 to 8 newtons. All right, we also know from Newton's second law that acceleration and mass are inversely proportional. So remember, that means when one goes up, the other goes down. And it changes by the same factor. So if one doubles, the other is cut in half. So on the next screen, we'll create an acceleration versus mass graph representing this relationship. The graph for an inversely proportional relationship, like we see for acceleration versus mass, is going to show that as one variable increases, the other decreases, or vice versa, as one decreases, the other will increase. So let's draw this. So this is what your graph is going to look like. It's going to look like a curve, and let's just pick values on here like we did for the last graph. Let's start down here this time with a mass of 8 kilograms, which is showing an acceleration of 2 meters per second here. And this time, let's decrease our mass. Let's cut it in half. So cutting 8 in half would put us at 4 kilograms, which is right here. If we cut our mass in half, we would expect that our acceleration doubles. So again, when our mass was 8 kilograms, our acceleration was 2 meters per second. We cut the mass in half to 4, and if you follow this over, we see that our acceleration did indeed double. Okay. We can choose acceleration, for example. If we double our acceleration from 4 to 8, that would put us here on the graph. Doubling our acceleration, we would expect our mass to be cut in half, and we see that it is if we follow this line down, okay, that it is decreased by a factor of 2 or divided by 2, so now we have a mass of 2 kilograms. So let's put Newton's second law into action here with some problem solving. When you're doing these problems, keep these things in mind. For each problem, a different net force equation is needed. We are going to create our own equations based upon the given information, and all equations written are different for each problem. You have to take into account all the different forces acting on the object. So keep in mind that an equation that's written for one problem may or may not work for a different problem. So the next part is actually using this to solve a problem. And so when we solve problems after we write our givens, we need to make sure we draw a picture of the situation with all the forces acting on the object. So in this particular problem that you're given, you see a 20 kilogram crate of physics books that is sliding across the tile floor. I know that that 20 kilograms is a measure of mass, so I'm going to list mass equals 20 kilograms underneath my givens. It tells me that I apply a force of 50 newtons to that crate. Now, that force I'm going to label FA. A just simply referring to my applied force. So FA is 50 newtons. Okay? And it also tells me that the force of friction acting on the crate is 30 newtons. So we're going to call that FF for the force of friction. Okay, and again, that is 30 newtons. It wants to know how much is that crate accelerating, so we'll list that as our unknown in our given information. Okay? So let's draw all the forces acting on this box now. I know that the box has a mass of 20 kilograms, and we learned that if something has mass and it's in a gravitational field, it's going to have a weight. So Fw, which we know is going to be equal to m times g. Okay? We also know in this particular problem that it's sitting on a tile floor, and so it's also going to have a normal force, which we know is equal and opposite, so we'll label that Fn. I know that I have applied a force of 50 newtons to this crate, and so we can label that on the diagram as well. Now it doesn't specify which direction I'm pushing it, so I'm just going to assume that I have applied that 50 Newton force in this direction. So there's my FA. And I know that friction opposes the direction of motion, and so if my FA, my applied force, is pointing towards the left on this picture, my force of friction I know is going to be pointing to the right. Okay. Now, the next step that we'll see on the next slide is going to be to remove any forces that do not affect this problem. And so when we look at this problem, I see that my force of weight and my normal force are equal and opposite to each other. And so essentially what I can do is just eliminate them from the problem. So I'm going to be able to get rid of that and that, which you'll see on the next slide. Alright, so once I have my drawing simplified and I've removed any forces that aren't affecting the problem, it leaves me with this right here. So I've got an applied force acting on the box as well as the force of friction. We can then write an equation to solve for the net force acting on the object, and so since I know that these two forces are going in opposite directions, to find the net force, I simply subtract the two. So I take my force that I'm applying to it, the larger force of 50 newtons, and I subtract from it the force of friction. Okay? What we can do then is substitute that information in to replace the unknown variables. So if I take my overall Newton's second law equation, which again states that F net is equal to mass times acceleration, I can substitute in FA minus FF for F net. And so that's what you see here in this box. Okay, I've just taken this value and substituted that in for F net. I'm ultimately solving for the acceleration, and so then I just rearrange this equation by dividing each side by m. So our final equation that we would end up with after we rearrange is that acceleration is equal to the applied force minus the force of friction divided by m, or in other words, 50 newtons minus 30 newtons divided by 20 kilograms, because our box was having a mass of 20 kilograms. So 50 minus 30 is 20 newtons divided by 20 kilograms, and when I divide that out, I end up getting a final answer of 1 meters per second squared. Okay? Now the units can be a little tricky, but if you remember that 1 newton is equal to 1 kilogram times a meter per second squared, and I would substitute that in for the top. Okay, so 1 kilogram times a meter per second squared. My kilograms are going to cancel out, and it leaves me with meters per second squared, which is an appropriate measure for acceleration. Okay, in this particular problem, you were pulling a sled with your new pony, and you don't want to overwork her, so you have to see what the force of friction is going to be. And so the givens in this problem, it tells you that you have your 50-kilogram little sister that you're placing onto the sled, so we'll list that as the mass. And it tells you that when you do that, the pony can accelerate the sled at a rate of 2 meters per second squared. Okay, so there's our acceleration. And when that happens, it's due to the fact that the force being applied by the horse is 300 newtons. Okay, so we'll list that as our FA, 300 newtons. And we're solving for the frictional force. Okay. All right, so let's draw ourselves a little picture here. Okay, here's your new sled. There's your little sister. Okay, and this sled is going to be hooked to a horse. Okay, so there's your horse. Okay. Now we know that this horse, like it said, is going to pull with an applied force of 300 newtons. And remember, we know that the force of friction is going to oppose that. Okay, so we would have friction moving in this direction. Okay. Now a key concept here is we know that that horse is pulling and creating a positive acceleration. So what that tells me is my applied force of the horse has to be greater than the force of friction. And so when I write my F net equation, I'm going to take my larger force, in this case my applied force, and subtract from that the force of friction. Now I don't know what my F net is, so what I have to do is substitute in. So if you remember, F net is equal to mass times acceleration. So I'm going to take this part of the equation and substitute that in for F net, which is going to give me MA is equal to my applied force minus my force of friction. Okay. Now I need to solve for the frictional force, and it's a negative on this side. So what I'm going to do is just add it to each side, which would give me FF over here. Okay. And then what I'm going to have to do is subtract the mass times acceleration. And so when you rearrange, your formula will look like this. Okay. And so my force of friction is going to be equal to 300 newtons minus the quantity of mass, 50 kilograms, times the acceleration of 2 meters per second squared. Okay. And when you do the math here, 300 minus 50 times 2 is 100 is going to give you a frictional force of 200 newtons. Okay, now notice that I substitute in 1 newton for 1 kilogram times meters per second squared, which I see over here for my mass times my acceleration. So overall, that leaves me with a force of newtons. Okay, in this particular problem, you're going skydiving, and the only number that it really gives you in this problem is this 850 newtons. Now, it tells you that that is what your tension gauge reads, which is caused by the air resistance from that parachute opening. And so we can think of that air resistance as providing the frictional force, which is slowing your body down from being in complete free fall due to gravity. And so it's very helpful in this one to draw a picture. So here's your little parachute. Okay. And we know that that air resistance caused by the parachute is going to act in that upward direction. Okay. Now the key to this is this part of the problem right here. We see that once that parachute opens up, you feel as though you're moving at a constant speed. And so my hint to you for class tomorrow is keep in mind that at a constant speed, we know that acceleration is equal to 0, okay, which also means that our overall F net is equal to 0. Okay. And so see if you can solve for this problem and figure out your approximate mass. Okay. You also have a bonus opportunity here. So if you can solve for this problem with everything being correct, I will give you 2 points added onto your quiz.